Okay, so I'm Nullity. I'm a zero knowledge security researcher at yAcademy. We run fellowships. Previously, we've had 5 smart contract fellowships, and just now we wrapped our second ZK fellowship. And yeah, I'm here to talk about this thing called Halo2. So let's get started. We'll brush up a few basic terms and then we'll move on to Halo 2. So before we dive really deep into Halo 2, we'll have some background on provers and verifiers and constraint systems. So, it doesn't feel odd to get those terms in Halo 2. So typically, when you read any zero knowledge protocol or any introduction to zero knowledge protocols, you see that there's a prover and a verifier, and there's an interactive protocol where the prover tries to prove something to the verifier. It could be any computation like basic math, like is the addition of two numbers the third number, or is the hash of a string some other string or a hex. So the prover tries to prove some logic, and the verifier is there to see if the computation has been done correctly or not. Most zero knowledge protocols, introduction to zero knowledge protocols or interactive protocols start that way. But in reality, a lot of protocols, zero knowledge protocols, are non-interactive in the sense they are computer programs. So the prover and the verifier over here are not people or characters such that they can interact, but computer programs such that they face a lot of computational difficulties and are and have limited resources and constraints. So in reality, you would build up a circuit which encodes all your computation, and this circuit would then produce a proving key which is given to the prover, and the prover tries to generate a proof which would be an uncomprehendable bunch of alphanumeric characters and just some gibberish, which is then given to the verifier, which then tries to make sense of the proof which was received by the prover. And all the verifier does is it gives a yes or no. Yes in the sense, yeah, the proof is correct. No in the sense that, no, this is not the right one. So in reality, there is no interaction between the prover and the verifier. Let's focus on the part where we generate the proofs. So the proof generation process is just this part where you take the circuit and you give it to the prover and you generate a proof. This part can be then broken down into multiple steps. This is like a basic building block of proof generation. There are even more minute steps, micro steps, I would say. So here you have the circuit, which is then broken down into a constraint system. A very popular and known constraint system is the R1CS constraint system, R1CS, which is rank 1 constraint system, which is here on the screen if you see. Uh, then the constraint system is broken down into polynomials, and then you run operations on those polynomials, and then finally you get a ZK snark, which is your proof. So yeah, we know what a circuit is, but we haven't dived uh, deep into a constraint system. Yeah, if you guys are don't have a clear understanding of what a circuit. Mm-hmm. Okay, yeah. Yeah, if you guys don't have a clear understanding of what a circuit is, it's just a computer program where you have the logic which you are here to prove. So, constraint system, and specifically R1CS, rank 1 constraint system. Rank 1 constraint system is this set this constraint system where you can express a logic in terms of addition and multiplication only. So you can have any logic, but in the end, you have to boil it down to one of these two operations. For simple programs, this is much easier, but for complex ones, this becomes pretty difficult. Um, let's have a small example. You might be familiar with Circom, or if you have an electrical engineering background, you might be familiar with what's that thing? Verilog, the HDLs and like the digital circuits where you have the wires and the inputs and the outputs. So here we have one such circuit where we have three inputs, A, B, and C, and we have one output D. What we do is we multiply A and B and we add C to the product of A and B, and that's our output. Now, this is a pretty simple program, and this is best when it's done in the R1CS constraint system. But let's say you want to divide two polynomials, or you want to calculate the um, the hundredth square of some number. I don't think that would be feasible when you have R1CS. So clearly, there are shortcomings in R1CS, and they can be stated as there's no support for custom gates. So there's only addition and multiplication. You cannot express your custom computation of function. Uh, I mean, not every function or computation can be boiled down to multiplication and addition. I think um, that's bad. And there are no lookups. Typically, in all the computer programs, when you're running programs, lookups are pretty useful. And the third one is R1CS systems, like GROT16 is this proof system, and this proof system uses R1 rank 1 constraint system, and this one requires a circuit-specific trusted setup, meaning that every time you build a circuit, you would have to do a trusted setup for that circuit. So R1CS was, I think, used back in 2016, and GROT16 was used back in 2015, 2016, when the Zcash folks were using sapling and they were coming up with techniques to do shielded transactions in Zcash, and the people of Zcash obviously noted these problems of these three problems. That is the lack of custom gates and lookups and this trusted setup issue, and they thought they would come up with a new proof system and a constraint system. So they created Halo2. So it's Sean Bowe, Dara Hopwood, and Jack Gregg, who then created Halo2 to facilitate shielded transactions in Zcash. And it used a different constraint system called plonkish arithmetization. Now, what is plonkish? Yeah, in R1CS we saw this logic where we had A into B plus C. Seemed very simple. In terms of RMCS, this would be broken down into two equations. First, you would calculate the product of A and B, and then you would add that to C. So, not everything is done in one single step, and this kind of takes a lot of time and space, whereas we have limited resources. Enter plonkish arithmetization. So this is an equation. At first, it looks scary and you can't even read it. But once you get a hold of this is really awesome, and you can do great customization with this equation. So the equation on screen is the bare bones of plonkish arithmetization. Uh, and yeah, you would see a lot of Qs. There's QL, QR, QO, QM, QC. All these Qs are called selectors, and selectors, in the sense you can turn it on or off depending on your equation. And the values, there is XA, XB, XC, and the X values are all inputs and outputs. So this equation you see on the top is created on the assumption that you have two inputs, which are XA and XB, and one output, which is XC. Now, how do you bring life to this equation, or how do you use it? Yeah, let's say you wanna, let's say you have a very simple gate where you add two numbers and you print the output of it. The gate would be then a plus b equals c, where c is the output and a and b are inputs. So here our xa will be a, xb will be b, and xc, that is the output, would be c. So we have configured the values, the variables. Now it's time to configure the selectors. Now QL stands for left wire selector, QR is the right one, QM is for the multiplication one, QO stands for the output selector, and QC is for the constant selector. So here we'll say we have one left input, which is A, so we put 1. QR is 1 because we have one right input. Over here, right and left are, it is with respect to this addition operation. So to the left of your addition symbol, you have A, so it would be the left wire, and B will be the right one. There's no multiplication happening, so QM would be 0, and QC would be 0 because we don't have any constants like 1, 2, 3, or anything. So QC would be 0. And if you substitute all these values in the plonkish equation, you would get a plus b equals a plus b minus c equals 0, which is the original equation which you wanted to represent. So yeah, this is the this is what the selectors mean. You can take another example of multiplication. Let's say you have a multiplication gate and you want to express that one. So QM would be 1 here, and QL and QR would be 0, because QL and QR come into place only when you have addition. And the rest would be same, and you would get A into B minus C equals 0, which is the original equation you wanted to prove. Now, again, we are proving addition and multiplication. So is plonkish arithmetization just a glorified equation which has extra variables, or is it something more? Uh, so yeah, if you take an example of this equation, let's say z equals x into y cube. In R1CS, what we would do is we would multiply y and y once, and then we would multiply uh, uh, the square of y with y again to get y cube, and then we would multiply that with x to get z. So this one would actually span into multiple equations. This is in the case of R1CS. But in the case of plonkish, what we could do is we could take the bare bones of plonkish equations, which is this one, the first two lines, and we could add our own selector, which is q cube, and we can represent this part of y cube as xb cube, and we would be done. So this is the part where plonkish equations really stand out. You can add your own selector and your own computation, and you can customize the equation just however you want. So this part is the basic Plonk equation, and the one where we uh, where we had q cube. Q is the selector over here, and xb is the input. It would be y over here. So this is our custom addition to the Plonkish equations, and you can do this to any circuit without much of a hassle. So yeah, the advantages of the Plonkish constraint system is that it is very customizable. It kind of gives you a lot of control over your equations and your circuit. So yeah, you have a lot of customizability. And the second one is the concept of selectors itself is cool. You have granular controls, and you can create multiple complex structures based on these two properties. So yeah, we just had a look at plonkish arithmetization. Um, if you've got any questions, fire away.
Yeah, so we still can't like make gates that like correspond to bitwise operations in this Halo 2,
Which operation in specific? Can you give an example?
like any XOR gate or OR gate
You
specifically.
can. You can, but yeah, even with all the advantages of plonkish, um you can actually with a few tips and tricks, but yeah, it's not that easy right now in ZK. Yeah.
Yeah, I understood.
Okay. Yeah. Um. Yeah. So coming back to Halo 2, we just had a look at plonkish arithmetization, and then we know what Halo 2 is right now. It is a plonkish constraint system with a commitment scheme. So Zcash, the people who created Halo 2, they use a different commitment scheme called IPA, and the PSE folks who forked it from Zcash, they use KZG to for it to be compatible with Ethereum. And as you know, if there's a proof system, you have a commitment scheme and an IOP, and we use the Plonk IOP. So yeah, this is Halo 2 in simple words. So uh, in Halo 2, we would write circuits. We would write circuits using the Halo 2 API, and the inputs which we give to the circuits are represented in form of a matrix or a table. Even in R1CS, they are represented in terms of matrices. And in Halo 2, it looks more like a table because it's huge, and we use colors to segregate the types of inputs, which you would see just in a second. Yeah, so the Halo 2 system is now the Halo 2 table has three sections, which is you would see there's like a white one, a white column, then there are pink columns, and there's this blue violet columns. Each of these columns stand for something. So the white one are actually instance columns. Instance columns are public inputs which are shared between the prover and the verifier. So um, these are placed in the instance columns. The pink ones are advice columns, which contains your private values or witnesses, as we would say. And these values are accessible to the prover and not the verifier. And then you have the fixed columns, which are filled at the time of key generation. And most of the times, fixed columns are used by lookup tables or something which is known beforehand. Or yeah, as I said, that's pre-processed values. So the whole table has 2 to the power k rows, and I don't think there's a limit on columns, but yeah, you have 2 per k rows, but not all of those rows are usable. Usable in the sense you cannot assign values to some of the cells in the table. So the first 2k minus t minus 1 rows are usable. You can assign values to the cells. And the last t rows are called blinding rows because they contain blinding factors. Now, what is blinding factors? So blinding factors are these gibberish numbers, or uh, yeah, they are the ones which add the zk, the zero knowledge stuff, to the proof. So if you sort of remove the blinding factors, there wouldn't be zk to your proof. So it would just be proof of math. It wouldn't be a zero knowledge proof. So in simple words, for a proof to be zero knowledge, it has to be hiding and binding. And by taking away the blinding factors, you would take away the hiding property. So how do you fill in these values and where do you get these values? So you can generate these values by hashing the witness polynomials. Witness polynomials are the ones you get um, in the advice columns. So yeah, that is about blinding factors. And this is your Halo2 table. Let's go back where we started. We started with the whole truer verifier saga, where we knew that these aren't two characters but two computer programs interacting with each other. Um, and we would see that often in interactive protocols, there is this prover which sends a commitment to the verifier, and the verifier, to check if the commitment is right or not, sends a random R to the prover, and the prover has to evaluate the commitment at the random R and send back the commitment to the verifier. This is an interactive protocol which would happen in ideal situations, possibly in books. But in practice, in when we're dealing with programs, it doesn't work like that. So we have a prover program which would which would have this commitment of p. To get a random r, it wouldn't go to the verifier. It would use a hash function and hash the commitment with a bunch of other variables. Now, these variables are really important, and if you mess any of these, you can compromise the security of the zero knowledge system. So, the prover would hash the commitment and a few other variables to obtain a random R, and then it would evaluate the random R on its own and calculate the commitment at the random R and send it back to the verifier. So this process which you just saw is called Fiat-Tremere transformation. Fiat-Tremere is nothing but transforming this interactive protocol into a non-interactive one where there's no communication between the prover and the verifier using a hash function. And in books or in papers, this hash function is often referred to as a random oracle model. But yeah, this is enough information for us to go on. And yeah, this is how you obtain these blinding factors. You hash the witness polynomials and you put it in the last row of the table. Yeah, we've successfully completed um, the structure of how values in a Halo2 matrix or a table are represented. Now we're going to dive into the Halo2 API. And before we do that, do we have any questions?
Yeah, so for now you talked like there are 2 to the power k rows and t of them are not usable
Yeah.
because they, yeah, because they are blinding factors. So is
Mhm.
there any relation between like k or t, or like how many blinding factor rows we should have ideally, or
Yeah.
like we can increase it or decrease it?
Yeah, you can actually. There is this calculation. That's a nice question. It's usually less, and it's based on your based on your witness size. So let's say you have five witnesses, like five witnesses in advice columns. I think the T would be somewhere around 3. But yeah, there is a relation. There's not a relation between K and T, but there is a connection between the witnesses you give to the table and T. So T is roughly estimated of that. Yeah, I can share you the code where we calculate T, but I don't have it right now. Yeah.
Yeah, also in the Fiat Shamir model,
Mm-hmm.
what happens if the verifier itself is malicious and will like not accept even like our like commitments that we have?
That's a
Like
good
it
question.
will like reject our any like correct computation we would have done.
Mm. That's a good question. So, typically in ZK proof systems, what happens is that everybody runs their own prover, but there is one common verifier which is public, which is auditable by other people. So, if the verifier is malicious or has incorrect code, which can potentially um, destroy the system or stop the process and create a DOS, people would know that. So yeah, the verifier here is a public entity, and if it's malicious, we would know that, and that's the assumption here. Yeah.
Yeah. Okay, that's it.
Okay. Um, yeah. So let's start with the Halo 2 API. So far, we've had a look at how the Halo 2 table looks and how we would represent values in a table. But how do we actually assign values, and how do we calculate and create our circuits? So the Halo2 API has a few components. Um, let's start with the first one. Before that, the Halo2 table has, we talked about columns and rows, we didn't talk about cells. So the cells in the blinding rows are called as poison cells. So you cannot access poison cells, you cannot assign values to poison cells. The other cells, which are in the usable rows, are either assigned or unassigned. And the unassigned ones have a default value of 0, and the assigned one will have the value which you assign it to them. So a lot of times there are issues with the unassigned cells and the default value of 0. You would like face it a lot. So yeah, that's the cell. So we were about to start the components of Halo2 API, and yeah, let's start with chips. So chips are like functions in Halo2 API. They are like the basic building block. You can have multiple chips, or you cannot have any chip at all, and you can just have one big circuit with all the computation in it. So chips like ease the work you do. And inside a chip, you can create gates, you can define lookups, you can yeah, you can add all the logic you want inside chips. And usually there's like a chip config where you specify the inputs, the or the kind of columns the inputs would take, and the rest of the stuff, and where you would assign those values and regions. You then have a layouter. So once you have a chip is like a function. You would need a layouter to add the chip to the circuit and assign the values which come out of a chip onto the table. So this method, the assign region method, is the most common way of assigning regions. It's kind of the only way to assign regions on to the Halo 2 table, and the layouter is the one responsible for creating the shapes and the layouts and the assignments. You then have a floor planner. So what the layouter does, it would create shapes on the tables. These shapes represent regions, which are chips, which regions which use a certain gate. or which use a certain logic. Now, the layouter's job is to just assign these regions. The floor planner's job is to optimize the table itself, is to see the best way to arrange these regions such that we have the most optimal prover and the verifier cost. So right now in Halo 2, we have a floor planner called as a simple floor planner, and it uses this strategy called the first fit strategy to arrange these regions. And regions are in green color, like yeah, we have colors and everything. We have white, for instance. We have pink for advice columns. We have um, violet for fixed columns. So there's green for regions. So regions are the cells which are assigned. Yeah, why do we have to optimize? Why can't we just leave it as it is? So yeah, we are people who have computational systems with limited resources. So we obviously want a small proof and a faster prover and a low verification cost. So most people optimize based on their requirements. So if they want a low verification cost, they would have fewer columns, and if they want a low proving cost, they would have fewer rows. So that's the logic between yeah, that's a trade-off you have between cost and the number of columns and rows you use. So, zooming out, you have initially the circuit, which you would build using the Halo 2 API, and then you have the plonkish constraint system, and you can so whatever gates you have in your circuit are then broken down into the plonkish equation we saw earlier, and which is greatly customizable, so you don't have to worry like you do in R1CS. Then this is fed into the Plonk proving system, and in the end, you get your proof. Uh, because we have, because of the time boxed nature of this session, I haven't deep dived into Plonk because Plonk itself is like a huge topic with multiple rounds and a trusted setup, and yeah, it's huge. So, if you want to learn more about how Plonk works from the beginning, from the scratch, I would highly recommend going through this repository called Plonkathon um, in my GitHub, which kind of has a huge explanation of uh, how the polynomials are converted and the rounds in Plonk and how the final proof is generated. So, yeah, and if you want to learn more about Halo 2, I highly recommend looking out for yAcademy's second CK fellowship. We haven't made it public yet. It would be public in the upcoming weeks, and you can expect a lot of Halo 2 alpha there. Yeah, thank you to you guys for being so patient. And if you have any questions, feel free to ask.